Welcome back everyone. This is the final video in our PyTorch from Scratch series. So far we have learned tensors, autograds, the neural networks, the datasets, data loaders, evaluation, and even saving and loading the models. In this video, we're putting everything together and building a complete mini project entirely from start to finish. By the end of this video, you will completely understand how a real PyTorch workflow looks like. So if you guys are ready, let's go ahead and begin. So for today's video, we want to make our project predict a student's exam score based on how many hours they studied. So it's a simple example, but the workflow will be the same as many real machine learning projects. So let's go ahead and open our IDE and we can start coding it. So the first thing we need to do, as we usually do, is import torch, then from torch import nn, and from torch.utilities.data import dataset and data loader. So we import first PyTorch itself, then we import nn, which contains tools for building neural networks, which is where the nn comes from. And finally, we import the dataset and data loader, which will help us manage the data efficiently. And next, we can go ahead and start with creating our dataset. So we create a class student dataset and dataset. Then define init self. So self.x equals torch.tensor. Then we can put the hours they studied. So like 1. And for example, we can put 2. And let's just do 4 examples. 3 and 4. Then we can make the dataset for the exam scores, or the tensor as we call it for the exam scores. Torch.tensor. Let's say 50, 60, 70, and 80. Okay. Then we define the length, which will tell us how many samples we have, right? So define length self, return len self.x, which is the samples we have for the number of hours a student has studied. Then we define getItem self idx, and we return self.x idx and self.y idx. So this getItem function will basically tell PyTorch how to get one sample from each, right? So basically it will give one data point for a given input. So overall, this structure, it will be required for the data loader, which we'll use later on in our code. And here we just defined our data set overall. Pretty much we define this is the data set we have. So now let's move on to the data loader. So we can start by saying dataset equals student dataset, right? And data loader equals data loader Then we put the dataset batch size equals 2. So the batch size will basically say that we will process 2 samples at a given time, which is where we also did the get item from. We have 2 samples here. The X, one input from X and one input from Y, or output from Y. And shuffle equals true. So it means that we have a random order every time, so that the model doesn't just memorize the pattern, but it actually learns the pattern. So overall, as I just said, the data loader is just tasked with handling the batching and shuffling. The batching will just say or tell the model how many examples to learn from at once, and the shuffling, we set it to true, just helps the model generalize better. So now we can move on to our model itself, which is the neural network that we can now build it. So we say class my model nn.module. So then say define init self super init self dot linear equals nn dot linear. So this line 1 and 1, and I'm sure we have covered it before in our videos, basically says that the one here, which means we give one input to the model and we receive, or we are expected to receive, one output from the model. This is the nn linear 1 and 1. This is the meaning. And this is just based on our specific example that we're doing, but of course this can be way higher and different numbers. Then we do the forward function self x return, add this. Okay, so return self.linear x. And basically the forward function, it just defines how the data flows through the model. So for more information on this, you guys can visit our previous videos where we define the forward function in more detail. And moving on, we can now start the training setup. So we go ahead and do model equals my model, which we just created. Then we say the criterion equals nn.mse loss. And this will just measure the prediction error for the model. Then we do the optimizer equals torch.optim dot sgd. Then we do the model dot parameters, and learning rate we can set it to 0.01. So basically the loss function, which is here, it will tell us how wrong the model is, and the optimizer will update the model's weights based on how wrong the prediction is. So we are expecting the model to give us a more accurate output each time we train it. So together, these will both allow the model to learn. And now that we have the training setup ready, we can start the training loop. So we can say, first we will reset the gradient. So let's just write the loop. So for epoch in range, let's say we run it 100 times. For X batch, Y batch in data loader, optimizer dot 0 grad. So here we just reset the gradients each time we run the loop, so we don't just keep using the same ones. Then we make the predictions. So predictions equals model x batch. Then we calculate the loss based on the predictions. So we make the loss equals criterion prids y batch. And we back propagate. So we just use the backward method. So we write loss dot backward. This just helps us compute the gradients we have. And finally, we optimize. Or we can say we update the weights, pretty much. And over time, as this loop keeps running, for example, it runs one time, it will have a, for example, say a prediction error or a loss function. And each time we run it, this loss function should be expected to start decreasing because the model is learning and it should be able to make a better prediction as it starts to train and learn more. So therefore the loss function should also decrease. Okay, so now that we have done that, we have just trained our model. And we did forget to add the print function actually. So we can just add the print so we can see how the steps go. If epoch, let's say 20 equals 0, print f, let's say epoch, and loss equals loss.item. Let's say to the second decimal. So now that we run our code, we can see. So at run number 1, the loss is very huge, 5089. Then at number 20 of the training loop, we have 98. Then when we run it 40 times, it decreased 78, then 48, and 46. So as you can see, first it was very huge, but as we train the model and as the model learns, the loss function starts to decrease more and more. Now we can start doing some evaluation and inference, right? So evaluation, we will just set the mode to tell PyTorch that we are no longer training so that we can save on memory and efficiency. So we can go ahead and write model.eval basically. This puts the model into evaluation mode. Then with torch.nograd, we disable the gradients for the efficiency and memory. We say new x equals torch.tensor, let's say 5 study hours, let's say here, because in our first list we did not include 5. We included 1, 2, 3, and 4, but we did not include 5. So the model is seeing 5 for the first time. It has not trained on 5. Then prediction equals model new x, right? So the core idea here is to test the model's training abilities on something it has not seen before. So the model trained on our inputs of 1 to 4, but it has not seen 5. So we want to test whether the model has truly learned the pattern that we want it to teach it. So we are trying this with 5, which it has not seen before. And print predicted score, prediction.item. So now we ask the model, what score should we expect if someone studies 5 hours? So we can see that it has given an answer close to where we expect it to be, right? So, because if we look at the original list, we see that, for example, 3 is 70, 4 is 80. So we'd expect 5 to be 90 or maybe 100. So it understands the range of score that we're looking for and makes a somewhat accurate output. And that's basically the core idea of evaluation and inference. So now we can move on to one of our last topics, which is saving the model, and after that loading the model. And this is pretty basic. So when we save the model, it will basically let us reuse the model later. So meaning we don't have to, when we close our, for example, device that we train the model on, we don't have to open the device and retrain the model. We just save the state of the model and later load this model, so we don't have to repeat the steps we do each time. So basically we write torch.save model.state dict, then we say student model.path, this will be the output, and print model saved. And a reminder here is that we save the model's weights, right? Based on the optimizer, we save the model's weights, not everything, just the weights. Now we can load the model. So let's create a fresh model. First, let's say loaded model equals my model, right? Just a fresh model. Then loaded model .load state dict torch.load student model.path. Then loaded model .eval, we activate the evaluation mode. And finally with torch .nograd, the output, well, it's a loop, so output equals loaded model torch.tensor 5. I'll explain all this in a second. And we print loaded model prediction, which will be out.item. So here basically what we do is we create a fresh model, then we load the model's weights that we saved earlier, just above here. Then we put the model in evaluation mode, and just similar to the inference we do, the prediction should match the original model. So if we run it now, we should see that the loaded model has given us a near perfect matching output that it just gave our original model. So we got 102 here, and in our original model we also got 102, and it's actually the exact answer because it's the same model, we just saved it and we loaded it into a fresh model, so it should actually be expected to give us the same answer. And this is the loading model, which is really important to basically make everything much more easier so that we don't have to keep repeating ourselves when we're doing machine learning. And that's pretty much it, guys. So we have just built a complete PyTorch project from scratch, and this exact workflow, it can easily be scaled to the real world AI systems, right? They're all based, the core fundamentals are based on this. And in future videos, we will move beyond basics and build more advanced models. And if you guys have any questions, please let me know down in the comments below. So if this video helped you, please consider liking and subscribing, and I'll see you guys in the next one.